Now, Radhakrishnan, ready with the so you can start from the slide where you stop.
Good afternoon to all. Today my presentation title Controllable Preparation of Nickel-Cobalt Sulfur on Carbon Nanofiber by Electrodeposition Method as an finder free and freestanding electrode in high performance supercapacitors. In the past several years, carbon-based material such as activated carbons, graphene, carbon nanotubes, carbon nanofibers are attractive, much interested in various applications due to the special properties. Among these carbon nanofiber, carbon nanomaterial, carbon nanofiber are a special class of material and much interested in energy, environment, and biomedical applications. The carbon nanofibers are majorly obtained through electrode spinning process. The key advantage of these carbon nanofibers are one-dimensional morphology, tunable size, mechanical flexibility, lightweight, and various functionalities, and etc. However, the major demerit of these carbon nanofibers are poor electrochemical property and low specific surface area. Hence, it is difficult to use for wide range of application. In order to use a wide range of applications, further these carbon nanofiber were modified with several nanomaterial. For example, in this slide, the nanomaterial initially titanium oxide and molybdenum disulfide has been modified over the carbon nanofiber by hydrothermal approach and then used for energy related application. In the second scheme of in this slide, they have used tin precursor mixed with polymer, which is used as a electrospun precursor for preparation of polymeric fiber and then subjected into thermal treatment to form the tin oxide nanoparticle decorated carbon nanofiber. Like this, there are several nanomaterials has been successfully utilized or modified over the carbon nanofiber and used a broad range of application. In this direction, here we have successfully prepared highly flexible carbon nanofiber using polyacrylonitrile crafted lignin as a copolymer through electrospinning process. This is the schematic diagram for the preparation of carbon nanofiber. Initially, the polyacrylonitrile crafted lignin used as a copolymer during the electrospinning process, followed by stabilization and carbonization at various temperature, because the carbonization temperature is playing a key role to tune the physiochemical property of the derived carbon nanomaterial. Further, the iron oxide decorated reduced graphene oxide has been prepared by hydrothermal method, which has been used as a negative electrode, whereas the carbon nanofiber has been further used as a freestanding electrode for the electrochemical deposition of nickel-cobalt sulfur and used as a positive electrode. This is schematic diagram how the electrode was designed for the asymmetric device fabrications. This is the FESM characterizations prepared at a different temperature from 1000 to 1200 and 1400. All the images associate clear one-dimensional morphologies and highly uniform without any peaks. Confirm the as prepared copolymer is highly useful for the preparation of high quality of polymeric fiber, and also the as derived carbon nanofiber at various temperature exhibit a flexible characteristic, which has been further characterized by various technique, including for example, the carbonization temperature majorly influence on the fiber diameter and conductivity of the fiber. Instance, when increasing the carbonization temperature from 800 to 1400, the diameter of the carbon nanofiber gradually decreased, whereas in the conductivity of the carbon nanofiber gradually increased. Further, the material has been characterized by XRD, FTIR, and then conductor measurement and various techniques. Finally, this in order to verify the flexibility characteristics of the as derived carbon nanofiber mat, we have performed a pending state up to 5000 cycles. It has it demonstrates a good flexibility up to 5000 cycles without affecting the seat resistance. So, which demonstrates that the prepared carbon nanofiber has a high flexibility and also mechanical strength, which has been used as a electrode, freestanding electrode for the deposition of nickel-cobalt sulfur by electrochemical deposition. In this work, we have used 1000-degree carbonization temperature derived carbon nanofiber for freestanding electrode, followed by different potential cycles by CV method has been employed for the deposition of nickel-cobalt sulfur. When increasing the potential cycle, The thickness of the deposited material also increasing gradually. And then we have preliminary characterized by various technique, and we have chosen the deposition cycle 40 has a optimum electrochemical properties. Hence, we have used this cycle deposited material for the fabrication of asymmetric supercapacitor device with iron oxide decorated iron oxide decorated reduced graphene oxide. This is the characteristic of the derived composite material by FESM and XRD, followed by the prepared both material individually characterized by electrochemical technique to understand the charge storing property of the material. For example, initially we demonstrated CV for the nickel-cobalt sulfur deposited carbon nanofiber by various scan rate. We have observed clear Faraday behavior due to the redox characteristic of nickel and cobalt. Similarly, the same electrode has been used as charge discharge test at a different current density. We have nearly observed 790 Faraday per gram at 1 ampere per gram current density. Further, that Fe2O3 decorated reduced graphene oxide used for the detailed characterization under 3 electrode configuration. We have observed maximum specific capacity of 300 Faraday per gram at applied current density of 1 ampere per gram. Finally, we have fabricated using the nickel-cobalt sulfur as well as the iron oxide decorated nanoparticle has been used as a positive and a negative electrode using 10 molar sodium perchlorate as a electrolyte, because our aim to increase the energy density due to the high concentration of sodium perchlorate. We can go more than potential of 2 volt working potential. In the first CV, we have optimize the potential window of the fabricated device to tune the different potential window, and observe 2.4 volt is optimum for the fabricated device. Hence, we have used this potential window for further detailed studies. Then in the second slide, we have demonstrated different scan rate effect. Each scan rate, the increasing current density also gradually increase when increasing the scan rate, and also observed high integral current area, which demonstrated a high energy storing performance of the material, followed by the charge discharge characteristics was performed at different current density. We have observed maximum specific capacity of 70 Faraday per gram. Further, the stability we have measured up to 5,000 cyclics at applied current density of 3 ampere per gram. We have observed almost 92% capacity retention even for 5,000 cycles. And then we have estimated power energy density as well as power density. We have observed the maximum energy density of 56 watt per kilogram at power density of 1200. In final, we report the simple and efficient approach for the fabrication of asymmetric supercapacitor device using carbon nanofiber as freestanding electrode. A thin coating of nickel-cobalt sulfur film was successfully deposited by electrodeposition method over the carbon nanofiber and utilized as positive electrode. A highly uniform iron oxide nanoparticle decorated with reduced graphene oxide was obtained by the special hydrothermal approach and utilized as a negative electrode. The fabricated asymmetric device delivered a high energy density of 56.3 watt per kilogram at power density of 1200 watt per kilogram with the excellent cyclic stability up to 5,000 cycles. The present flexible carbon nanofiber synthesis method and modification with good electrochemical performance opens a new avenue for a novel preparation of various nanomaterial modified flexible carbon nanofiber for future energy related applications. I acknowledge this work for project funding and organizer and our institute. Thank you all.
Thank you, Dr. Radhakrishnan. Please join me. Yeah, so with this, I thank each and everyone who had participated in this speakers. So thank you all once again. Have a great day. Close the session.